Okay, yes, hello. And yeah, thank you very much for having us. As kindly introduced, my name is Toby and I'm a data scientist and optimization developer with a background in mathematics and statistics. And I'm here with Philip, who I'll just let introduce himself before we kick off.
Yeah, thanks, Toby. So yeah, similar to Toby, I'm a data scientist at Water Corporation, working as an optimization developer and sorts of different analytics here, with a background in mechanical engineering, physics, and maths at university. But yeah, looking forward to sharing what we've done today.
Cool. Thank you very much. Yeah. So as Philip said, we are from the Water Corporation in Western Australia, and today we're going to be showcasing one of our optimization models we've built for scheduling groundwater abstraction. Cool. So before we get into the problem, I'll just give a quick intro to who we are as a corporation, our analytics team, and then give some context about how we actually supply the water. So Water Corporation is the state-owned utility in Western Australia, and we provide water, wastewater, and drainage services across the state. We have over 4,000 employees and contractors to service over 1 million customer connections, which makes Water Corp one of the biggest utilities by coverage in the world. And Phil and I are part of the advanced analytics team over here, where we have a big focus on all things optimization, data science, and data visualization. And that's WA highlighted on the map there, and we are based in Perth. Now, the model that we're going to go through today sits in the water supply space and was first developed for the Perth metro area. We have since rolled this solution out to other areas, but for this presentation, we will focus on this metro area. In Perth, we produce and supply approximately 300 gigalitres of drinking water every year, and there's over 2 million consumers in this section. And some of that water is also exported to other regions of WA. The Perth integrated system, we have 15 dams, 6 groundwater treatment plants, which are fed by over 160 bores or wells to get the water out of the ground, and 2 desalination plants with a third on the way. Last year, almost 50% of the drinking water in this area came from groundwater. And now groundwater is our most sustainable source, so it makes sense to use as much of it as we can. And this groundwater process is what our model is optimizing. Cool, so this is the groundwater process. The water is contained in different aquifers under the ground, and those vertical gray pipes that you can see represent bores or wells that we use to abstract the water. How much water that we can abstract from the ground is restricted by licenses from our government. And across the 160 metro bores that we have 48 different licenses, which total around 155 gigalitres per year. And these licenses are grouped by the different aquifers or how deep that the bores reach underground, or they're grouped by geographical location. So the bores, if they're example near the ocean or near some wetlands or perhaps some other sensitive areas. Okay, that's enough context. So let's look at the actual problem that we are optimizing. So in the groundwater process, we have our bores, and each of those bores has their own flow rate, quality parameters, licenses, maintenance schedules, and many more parameters that are unique to them. We extract the water from these bores and we send it to a treatment plant to improve its quality and make it drinkable. Some of our treatment plants also have 2 different or multiple treatment options that we can have to choose between, each with their own costs and treatment strengths. From there, the water is ready to be pumped out to customers, and there is planning and modeling that tells us how much water we need as this demand. So we can follow this demand profile back through the process and it becomes our target production out of the treatment plant. So the problem then becomes we need to come up with a schedule of turning these bores, these different bores, on and off throughout the year to meet the target demand. And at the same time, we also want to know how much water we should be sending through our different treatment options at the treatment plant to minimize costs there. So historically, this was done using a spreadsheet that looks something like this. And as you can imagine, optimizing something by hand did not necessarily produce the best results. And often the planner's strategy would just resort to this really greedy approach where they would just use the bores that had or use the easiest bores. So the ones that had the most licenses remaining, or the ones that had the best water qualities, because they were just easy to work with and easy to blend together. They then had to monitor their system and just do little tweaks reactively to stay within some of the constraints. But so this was a functional process, but it was also very manual and very time consuming. And obviously there was no guarantee that the plan that they actually came up with was an optimal one. It was also not very dynamic. So when things didn't go to plan, or if conditions changed and people deviated from the plan, the rest of the plan that you might have produced at the start of the year could become infeasible. And that would mean you have to start this planning process all over again. So the business were thinking that there must be a better way of doing it. And that is when the problem came across our desk. And I'm just going to hand over to Phil.
Thanks, Toby. So the data analytics team, we became aware of this challenge and proposed a potential methodology to solve it using mathematical programming and optimization techniques. Solving this bore scheduling problem is like trying to solve a multi-dimensional game of Tetris, if you can imagine that. The initial work in a master's project found that with all the strict requirements involved, it was over-constrained and impossible to solve. However, many of the business rules we codified are more fluid, so there's variations and changes that are allowable, but through our modeling, we're not captured. So we need to be flexible to achieve operational robustness to reach an acceptable solution. We need to work in the real world with our model. So if we formalize the problem, our goal is to produce an optimized groundwater blend such that the production volume is maximized and chemical treatment costs are minimized whilst meeting all business rule requirements. To model, we codified the business rules into mathematical constraint expressions, applying reasonable assumptions and simplifications where we could. This was all done using a mixed integer programming methodology, which has been used in similar industrial scheduling problems from our reading. One key thing through the project has been the importance of stakeholder engagement to regularly engage with the operational planners and others to understand the processes for modeling. Identification of edge cases and exceptions to constraints was quite iterative. As much as you'd like to gather all the information straight away, often the process has been thought of in such a, often hasn't been thought of in such a precise way. Most of the planners don't know the exact equation. They just know this thing has to happen and this other thing cannot happen. And then that's our job to make that into equation. And just on the screen, there's a few photos from when I traveled down to Dunsborough, 3 hours south of Perth, to talk with the people at the water treatment plants as an example of engaging with the people at the ground. And this greatly helped with the purpose of modeling these processes. So I've mentioned this model development process. We see it as there's quite a refined kind of set of steps to take. So initially taking all the information and documents from our stakeholders is the first kind of step towards getting our model defined mathematically. They have spreadsheets, they have operating strategies, they have plans. We can often get quite a bit of information from that. So we identified a lot of the core considerations of the objective and constraints and define them in words. So this asset must only be on once every 2 weeks. or some other kind of element regarding maintenance. We then look to prototype the model on paper. So this is where we start to write out the equations of state and check for edge cases to ensure robustness. So we may define a rule, however, if there's a certain instance that doesn't meet what's required, that's going to fail, and the stakeholders will be able to identify that quite quickly. So getting that feedback from the stakeholders is really important to confirm we have modeled the system accurately, and then taking our equations and writing that in code and try and inspect the results. If the model is feasible, often that is the hardest challenge if you've got a very tight model. Following this, we aim to get further feedback from our stakeholder to review the results and check if they are logical. They can often identify these issues really quickly. So if you provide them a plan and they're like, no, this cannot be done this way, they will see that straight away. But it's often more difficult to define those exact rules to prevent issues occurring. So there is a bit of iteration across this process. And on the screen there, we've got a photo of the whiteboard of writing out all the equations and prototyping the model as we go. So from all that work, prototyping and developing the mathematical model, we developed the model constraints. So this model has lots of different constraints as listed here. So just mentioning a selection relating back to what Toby's described in the context. So we have our bore groundwater license and allocation, these limits from our regulator per year, the water quality, ensuring that the mass balance of the raw water blend meets a specific limit. So just a simple kind of chemistry consideration there. And the demand, ensuring the volume extracted is close to the target within the upper and lower weekly limits and meeting the defined annual lower bound. And there's more there on the screen. You can have a read through. These all define the feasible regions for solving, and we like this diagram. I think we've referenced this off some Gurobi documentation, that kind of idea of cutting the plane with the different constraints. So the more constraints you have, the harder it is going to be to find a feasible solution. Getting the right constraints for something as fundamental as even, but the time logic was not immediate for us. So we had an original formulation, we had to change that as further extensions of the model were required. So we'll touch on that a bit later as well. But yeah, lots of constraints in this model, and then lots of auxiliary variables to kind of enable additional functionality where required. The favorite of modelers, non-linearity. So ideally we do not want non-linearity in our model, but we had to make an extension to the model that required non-linear constraints. So this was where we simultaneously want to optimize which bores we are activating, as well as how we treat them in a given week. So hopefully that diagram kind of explains, yeah, we want to choose which bores and then how to treat them. However, both of them are dependent on each other. So that's where the non-linearity comes into it, especially when we consider water quality. So the purpose here, as I kind of touched on just before, is to match that inlet water quality with the requisite treatment strength. So the stronger the treatment applied, the higher the cost. So we want to reduce costs as much as possible, but sometimes that water quality coming in is less than ideal. So you have to provide that stronger treatment. So it's not a case of, oh, we'll just ignore that and avoid it. But we can minimize it to what is required. So rather than just applying the stronger treatment because it is safer to do so or it's reducing the risk, let's find the optimal for that. And this dual choice provides greater flexibility for our plant operations. We looked at different ways to model this to try avoid non-linearity because it makes the model a lot slower to solve, becoming quadratic, but we weren't able to do that. So yeah, we just hit a non-linearity we couldn't avoid. So we had to deal with that. And just finally, from mentioning all these constraints, show just a preview of, if you can bring that up, Toby, of the mathematical model. So all different equations. We're just really showing this to show that all comes back to that formulation and the algebra. And generating an equation from a business rule takes a bit of work to get just right, as I mentioned before. And you can see there's just lots of little things combined together. And it's good to have this formulation to lean back on. So if you're reviewing your code, you can check, oh, have I actually implemented that correctly? Not just going from your mind straight into the code. It's good to have this reference point with the equations. The combination of these expressions with the decision variables does yield a large set of equations to solve, as mentioned on the screen, many thousands. And that's where we need something to implement in code to solve this. Yeah, I'll leave Toby to describe a bit of that.
Cool, thanks, Philip. So I'm just going to go through a little bit of the tech stack that we used in this model. So Python was our programming tool of choice for all our things: data processing, model creation, model deployment. Almost everything we did was done with the help of Python. I mentioned Pi there. We collect our operational data directly from our Pi time series historian, which allows us to have a really quick automated response to when things change in the system, and really avoid a lot of manual data updates and things like that. And of course, the core to solving our model is, of course, Gurobi, which is why we are here today. We are making use of the Python APIs that Gurobi supply so that we can keep all these tools in one place. We have also developed a nice user interface in a web app to give a few degrees of separation between the users and code, because we don't want our users running code directly, whilst also trying to give them a good user experience with the model. So it's here that the users will tweak some of their input values, and they'll click run, get the model, and even see some preliminary results. And for this, we've used the React framework for our front-end app, and using a Flask backend. I'll also note here that all this development we did in-house, and I think we've had around 3 developers on and off at any given time over the years, but that's not at a full-time capacity. Cool. Okay, so once the model solves, we then create some more detailed visualizations to share with our users using Power BI, as we find it an easy interactive visualization tool. So I'm just going to take you through some of those inputs and explain them. Right, so this view that I did show a little sneak peek of earlier is the view that we actually give to our operators. So this is what we hand them to implement our optimized schedule of the bores. So it's really just a timetable, and we've got our different weeks across the year across the top, and each of the bores in the modeling process down the bottom, down the rows, sorry. And the values will show each week which bores are on and off, as well as how much that we should extract from those bores. And we've also got some fancy highlighting in there to indicate different bore statuses. So if a bore is in maintenance, or if you are forcing a bore to be on, we account for these things too. Here we show our target demand. So this is the demand profile that we have to try and meet out of our treatment plant. From the bore field, you can see in the top graph, the stacked columns are the individual bores that make up that demand, that target production profile. And then in the second graph there on the bottom, you can also see the breakdown versus the different stream options that we mentioned before. So our treatment plants will have different treatment options that we need to choose between, some more expensive than others. So we need to optimize for that as well. This is a good view for our regulators. So this is all things to do with our licenses. And so we can make sure that we aren't doing anything that we shouldn't. So in the top right, you can see this is a breakdown of how much water we're abstracting across our licenses as a whole. Our goal is to get as much water from groundwater as we can. So you can see there, this particular model is achieving 99.8% of the license available, which is quite a good outcome for this. And before we had optimization by hand, they were getting not anywhere close to that number. Cast your eyes to the box on the left. You can see this breakdown of the abstraction by the individual licenses. So I mentioned there is multiple licenses, so you can keep track of them there. And then finally, the graph at the bottom gives us the breakdown of how much we're abstracting from the individual bores. And if those bores themselves have an individual license, then we can keep track of that here. And finally, probably one of the most important outputs is water quality. So it's here that we can show our different water qualities over time and how they all blend together so that we can make sure that we are on top of that and providing good quality water. So for example, if you take water hardness as a quality, and that's the one in the top right, we can see that it's a bit hard to see, but there's the dotted purple line there represents our limit. You can see the raw water blend in the light blue columns, which is above that limit. But as we're treating this water and also optimizing for that, you can see there's this dotted orange line as well, which is it's our post-treatment quality. And you can see that's nice and tightly below the limit. So this is the view that our planners will look at and just make sure that all things are, we're providing good potable quality water. Cool, so I'll just hand back to Philip for a bit.
Great, thanks, Toby. So I guess just a bit more about how we're using Gurobi. So optimize and why. So optimization solvers had only been used in only isolated instances in the history of our business. So starting off, we had no endorsed corporate solver. A generalized solver would get us up to speed and enable lots of different applications. We did start with an unnamed free product, but it was unable to solve more than a quarter of the annual plan. So we try run the model, start ramping up 1 month, it solved, 2 months, it solves, 3 months, it solves, 4 months, couldn't do it. That would not work for our stakeholders in operational planning. So on recommendation, Gurobi was purchased and is being able to solve our models most of the time. So further work with performance tuning and later versions have enabled us to solve almost all of these problems. Sometimes we get infeasibility, that's due to inputs, in the order of seconds to minutes. So we don't have to run these overnight. The modeler can run it themselves through the user interface and get feedback within a few minutes to see if what they've run is feasible, and then also if it is an optimal result. Gurobi has now been used for other projects in the optimization space here at Water Corporation, and we have changed to a cloud license, which along with our user interface makes it much easier to deliver for our users. So I mentioned before, like sometimes the model doesn't solve or sometimes it's a bit slow. So one way we've improved performance and model stability is in its formulation. The original model had what's defined as a weak formulation, and some of it was unnecessarily complex for specifically the time variables, time constraints, just the notion of like week to week within the model, because it focused on a very specific constraint that we later found was less important than originally stated. It made some elements simpler to model, but it did cause big performance issues. Through necessity and the requirement for additional features, we carefully remodeled the formulation. This simplified some decision variables through introducing auxiliary variables to help with the complex logic. So from model implementation side, yes, it's more equations, it's more variables. However, it yielded a big improvement, big performance improvement for us. So I guess our learning from that is, if you're stuck with a model, our suggestion is don't be scared to try different model formulations. There's other ways to tune your model, but sometimes it can just be a fundamental how you've defined it. There's lots of ways to formulate the same thing. Yeah, you just have to try it sometimes. Another way we've improved model performance was through tuning the model solving parameters. The trade-off is often between getting feasible solutions fast or the optimal solution. Our original focus was feasibility. I mentioned before, it was like our impossible multi-dimensional Tetris game we're trying to solve. So yeah, we were focusing on that feasibility as we developed our modeling capability, but it really led to low quality solutions. So as we've matured, we had the need for further tuning. The initial tuning we did was simply by reading some learning materials, and through experience helped us, but only got us so far. We looked further into literature and the Gurobi documentation to inform us in other ways we could further improve it. One such element was the NoRel heuristic. This was identified as a good fit to this model due to the nature of the formulation and the difficulty in finding that initial feasibility. And this made a step change in the performance, going from quite a long time to almost instant feasibility at times, which, yeah, a few celebrations when it worked, the NoRel. To improve things even more, we've used the parameter tuning tool, an inbuilt method in Gurobi, to identify common parameters to be revised with our given tuning criteria. It's something we've done recently with one of our developers. That's been really good. We now set associated tuning parameters for specific models. So our models per groundwater treatment plant. And each of these associated tuning parameters for each treatment plant has stabilized the model performance to the best state so far. So we can reliably and repeatedly run these models and get a result. So yeah, our users are quite happy about that. And then getting to, I suppose, the bane of optimization developers is troubleshooting and feasibility. So a problem throughout the project has been trying to find, why is the model not solving? Why is it not feasible? Sometimes there's a bit of head scratching that doesn't always solve the problem, I mean. But there's, I suppose, a systematic way and different tools we can do to try and solve that. So as the models develop, and feasibility troubleshooting has been less of an issue because we understand the model and what are the sensitive constraints and inputs. So we have identified these different tools through this experience. The first case is through known user input issues. So for example, someone's put in maintenance, but also required that bore to run on the same week. So that's an instant fail in terms of feasibility. It's just an error they've made. So these are easy to understand and can be pre-checked in data processing. It's necessary to do this because there's just lots of different inputs. Our operational planners using this and are busy. People make mistakes as well. So having that diagnosis just makes it a lot easier to help them out and help us out in trying to determine the problem. Another tool we have used is the irreducible inconsistent subsystem, another inbuilt method in Gurobi. This allows the developers to analyze the results of the list of offending constraints if it can be produced in a timely manner. So often the IIS, sometimes it'll tell you it's like a handful of constraints, so maybe single digits. Sometimes the IIS will take minutes to hours to run. It just depends on the model we've got. So I suppose you can't use the same tool for everything when you're trying to diagnose infeasibility. So more recently, we've started using the inbuilt feasibility relaxation tools from Gurobi to determine the specific violated constraints and the amount of violation, which is more precise at identifying the problem. So it just takes a bit of analysis, I suppose, as we are learning how Gurobi works and different ways to analyze for infeasibility. Often we just hope the IIS would tell us exactly what's the problem. But yeah, having this different method with the built-in feasibility relaxation just takes a bit of analysis. But once you know the methodology behind it and how to diagnose it, it makes it a lot easier to look at it that way. So yeah, really glad we've had that recent addition. And I'll just comment on the old way we used to do it. Sometimes it's an easy habit to fall back into what I've termed constraint hunting. So very time consuming. You're hunting around for what's violating in your model, and it's a bit of a guess and check. So turn off a constraint. Is the model feasible? It will tell you something, but often if multiple constraints are offending together, so let's say, for example, the production requirement for groundwater and the license are both competing with each other, so the combination of those two constraints is infeasible, but removing one or the other makes it feasible. It'd be hard to tell that both of them are the problem. So you're just kind of taking a lot of time to determine something. So yes, you eventually will get there. But yeah, just from experience, it can be really painful trying to work out why your model's not working and seeing that effect on feasibility. Sometimes is an option, but yeah, now we've got these other tools and methods, it's a lot better. Just to touch on some further work in this optimization space. So from this project, this was our original in the team optimization model. We have gone further and looked at different projects. Water Corporation is enormous. There's lots of opportunities for optimization, but especially in this water space. So related to the groundwater optimization model, we've looked at planning scenarios for asset sensitivity, bore combination for intraday operation with a view towards energy savings, looking at the system, water transfer and production, network modeling, so connecting up all those water treatment plants and our dams and the desalination and the reservoirs, and looking at how all of that connects together and how we can optimize that. And something we're looking at a bit further now is into hydraulic consideration. So the selection of certain bores, they affect each other. They're not independent nodes just connecting to the central hub due to pipe work. And yeah, we live in the real world with physics, and having to deal with that does make it hard, but it is important to do that. So yeah, hydraulics is something we see quite a lot of scope to go further with. And something else we've looked to improve is our production demand forecasting. So we've previously taken data from other parts of our organization, but sometimes it doesn't always have the detail we're looking for. So we've looked to improve our forecasting using some data science techniques. So simple stats up to some machine learning models, nothing too complicated, but provides, yeah, a benefit to our modeling work. Another space we've looked at is energy use and cost. So it's something we've optimized. Water Corporation uses a lot of energy. There's lots of scope to go further with that, and especially if we're considering carbon emissions and yeah, all of those kinds of things. So lots of scope to go further. Just to summarize some of the outcomes and benefits from our work. So we like to think this is quite an innovative solution. So it's taking a big leap in capability here at Water Corporation and the industry for using mathematical optimization. We haven't seen too many other instances of using mathematical optimization in talking to other parts of Australia. I think we talked to someone from Florida and they might have done something similar, but yeah, not as widespread as we think it could be. We see there's improved automation in what we've done. So Toby mentioned before the spreadsheet. That's kind of awful to look at now compared to what we've got with our model. So all of these numerous data inputs, yeah, we can draw things directly from our time series historian and other sources just to make it easier for our users. Beyond just getting a workable solution, so from our feasible solution space through the optimization modeling, we can get the optimal choice based on all our constraints in a reasonable amount of time. I suppose, yeah, delivering optimization model, but yeah, again, comparing it to that manual method with the Excel spreadsheet, it's just a big leap. Something really important to our users is being able to be flexible. It's really critical due to the many dynamic changes experienced in operations. So a bore or well can become unavailable at very short notice. A treatment plant has maintenance, whether it's planned or unplanned. Being able to handle that has been hugely beneficial for the teams. On license compliance, we've been able to respond to the challenge of environmental sensitivity. So a lot of these drivers was due to the rainfall in Perth has reduced due to climate change. Our licenses are reducing. So yeah, that's where all the crunches occurred. So what we've done has significantly reduced the likelihood of those breaches to the license because we can plan out for the whole year and have that overview looking ahead. So there's some certainty there for the users that they know they'll be okay. It's not a week to week, will we get there or not? And just finally on chemical cost saving. So from a monetary perspective, being able to optimize the treatment has the potential to save quite a lot. Yeah, it's just understanding not just from a chemistry point of view, which has been the focus of how we treat our groundwater blend, but the decisions behind it. So yeah, that has the scope for quite large chemical cost savings. And that was all from us for today. I hope that's been interesting. I'd like to thank a few people who've been on the journey with us the last, 4 or 5 years, on the screen there. But yeah, really appreciate their help and contribution to this project. But yeah, that was all from us. I think it's time for questions.
Thank you, Toby and Philip. Now I'll just like to welcome back Gurobi experts Simran and David. We will start our Q&A sessions. If any of you have any questions, please feel free to post your question in Q&A. Simran and David.
Sure. Thanks both for the nice presentation. I think you've got a really cool tool, especially like the model and visualization. It's quite a tricky thing to do, and you've managed to do a really good job. There's some questions from the audience. So I'll start with what are some of the features which can be incorporated to further improve the model to become nearer to real world scenario? For annual planning horizon, is the local fauna and season considered when drawing out the groundwater?
Okay, so on the first part, so I mentioned hydraulics before, so that's come up quite a bit more. So yeah, one of the more recent projects we've done up in the north of Western Australia, it has, yeah, hydraulics are really a big challenge there. So we've actually combined EPA net hydraulic modeling software, and that connects up. In that instance, we have to have predefined combinations, because otherwise the hydraulic modeling requires the combination of bores to be predetermined to determine the flow, but the optimization solver needs that's the thing determining the combination, but that needs the flow. So our way around that was to kind of predefine combinations to include there. I mentioned so there was a mention about the flora and fauna. Similarly for that catchment up in Port Hedland, there's quite a bit of sensitivity around the environment. So we've actually looked to, this is where like balancing out the usage of the groundwater. So the groundwater will recharge over time, but if you use it for approximately like more than 75% of time, and if you don't give it a decent rest, so let's say at least 1 week per month on average, that will have a detrimental effect on the environment. But from an operator point of view, they're just looking at week to week. So the rollout of our tool is looking to help reduce that environmental effect. Yeah, a lot of it is dependent on the scheme. So in the metropolitan area, there's a lot more attention, a lot more knowledge about it, hence why the licensing. Out in the regional parts of country WA, it's a lot less well managed. So yeah, we're working towards that with the users, and of course it's a bit of a journey going from we just turn things on to this is how we have to plan it out for the whole year.
Just on the environmental sensitivity part of that question, I'll also just mention that we do have some considerations of that in the model. So we don't have to treat each bore in the same way. So accounting for environmental sensitivities on where it's located or something, we might want to deprioritize or restrict even further the abstraction from that bore. And so we do have a number of inputs that we allow our users to do to achieve that sort of thing. And that's flowed through to the outputs so they can make sure that it is achieved.
Thanks both. I'll take the next question. So this is from a student at a university in Singapore, and they're curious to know how the optimization model addresses the pain points of the greedy approach. For example, the lack of dynamism.
Do you want to take that, Toby? No, I can.
Yeah, well, I'll start. I'll kick it off. So I guess by hand, when you're doing optimization, it's not always the most straightforward thought to try and get a good solution. It can be hard to choose the right combinations, especially at the start. But what the solver does is that we don't have to. Well, I guess it takes the human element out of that. So it does it mathematically in the sense that actually, I'm going to hand over to Phil to finish that one.
Yeah, no problem. So I suppose with the greedy approach, I suppose for like a person trying to do it, understanding we have to manage water quality, save some water in the bank for later in the year, plus balance out all the different bores at once. It's just too many inputs to consider. So over time, someone would be able to learn how to not be greedy. And we say, when we say greedy, we mean they're taking the best water quality first, and then you're left with the things that are not as ideal. So they'd be higher in total dissolved solids, or the salinity is higher. What we're trying to do is balance it out so it's even across the year. So it's almost as if you like, in this instance, like you've got money in the bank, but you don't want to spend it all at once. So you want to save some money for the end of the year. So you're just using a little bit as you go, just as much as you need, rather than like, oh, well, I'll spend $50 on this big dinner, and then all the money's gone and you have to eat 2-minute noodles. Hopefully that's not too much of a weird analogy, but yeah, I suppose from that greedy approach, it's the same with the water, and that lack of dynamism. Yeah, often because of that greedy approach, as I mentioned, they get stuck at the end of the year. It's like, oh, well, we can't treat this water. It's not going to meet the Australian drinking water guidelines. We're going to have to use more desalinated water. We're going to have to use more dam water. And given in Perth that the rainfall's dropped off so much, we have to be really careful with water here. But the whole city is really conscious of don't waste water. And yeah, our communications here are really, really conscious of being careful with water. So as the people operating on the supply side, we need to also be really careful with how we do things.
Cool. Thanks. There's quite a few people thanking for the interesting presentation. And there is also 2 questions about what kind of nonlinear constraints have you encountered and how did you deal with them?
So there were simple hydraulic ones. Maybe Toby, you could bring up the equation slide. That might help. So it was really around that water quality. So because the water quality is a mass balance, but it's dependent on how it's treated, we need to know how much water was going to one stream, and then which bore is being activated. And because those two together, you just can't split them apart. So it's that combined decision making. So although it's like it's links in the chain, but there's that parallelization of the decisions in what we're trying to do. That's where that non-linearity came into it. So yeah, I think we had to turn on non-convex into the solver to make it work. But it was just a general quadratic equation that we had to solve for. But yeah, hopefully that made some kind of sense. It's yeah, we kind of looked at the situation. We took our original linear constraint. We then applied our treatment constraints we had to consider, combined the two, got it wrong a couple of times, then fixed that up. And yeah, we'd like, oh, this is non-linear, it's quadratic. We don't like this. Can we do it another way? No. Yeah. Wish we could, but yeah, not possible. Anything you want to add there, Toby?
Yeah, no, nothing to add there. I was just going to mention that, yeah, the bit about the non-convex that we had to thing, and that Gurobi does allow for some non-linear bits into it, but just does, yeah, makes it harder to solve.
Cool, thank you. Next question. So did you have to rerun your optimization model? And if so, what were the main reasons to do that?
Yeah, I'll jump in for this one.
Yeah.
So yeah, the short answer is yes, we do have to rerun this, and we have to run it quite often. But fortunately, with all the developments that we've done for it, we've pushed that to the user side, so we don't often have to see it. Now, in theory, what should happen is that our users will run the model once for a given treatment plan at the start of the year, and then they'll follow that plan through the end of the year, and everything works out fine. But we know that doesn't happen in real life. So I think Phil mentioned before, there are things that happen and creep up. So a bore might fail, or we might find that some of our assumptions about the given flow rates in a bore or the quality parameters we might find are wrong throughout the year, or they actually change throughout the year. So what happens is we find that the plan that we came up with at the start of the year is no longer feasible or it might be feasible, but it might not be optimal for the rest of the year as well. So we are constantly rerunning and changing and tweaking parameters as we get new information throughout the year. So I think typically we'll run the model, let's say about 50 to 100 times for each treatment plant throughout the year. And that's not all at once, but yeah, it does spread out through the year.
Yeah, and being able to rerun it is probably the main feature that's useful for our users, because yeah, run the plan for the start of the year. Oh no, something broke. Yeah, going to have to deal with that. So yeah, as Toby mentioned, regular rerunning. Sometimes we even do scenario planning of, oh, what if this happens, because they're trying to inform maintenance or different activities ahead of time. So being able to look at that forward forecasting is really valuable.
Cool. Got another question. So could you go into more details of the complementary data science techniques used and how they were incorporated?
I suppose in general, just having good data structuring practices, data reading. I suppose that's the more dry kind of things, but that's really helped in getting the models work. The other component is that forecasting using a little bit of a machine learning model, so we've looked at the trend of production demand, but we don't know exactly if it's going to rain, if it's going to be hot next year, is something going to be down. So it's just incorporating that simple model just to forecast what's going to happen next year. Is it going to be wrong? Yes, but if we forecast carefully, it'll be wrong less than if we just took the previous year. So try and include that trend in there. Any others, Toby?
Yeah, I thought I'll just expand a little bit on that forecasting, because that's predominantly when we see the classic data science tools being used. So just to name a few things that we've tried there, we are using some statistical methods, so the Holt-Winters methodology for doing some forecasting. We've tried some more classic ML algorithms like XGBoost and the like, some random forest as well, I think, in there to try and get that predicted algorithms. We've tried some ARIMA models and SARIMA models to do that forecasting as well. And it's just a matter of trying to choose the best ones.
I'll take the last question here. So did you use any heuristic to give a starting solution to your optimization model?
So we've used the No Relaxation heuristic from Gurobi inbuilt. I wish I could explain more how it works. It just does the right job for us. Yeah, I've done a little bit of reading about why it's good for our model. I think there's lots of clicks and different things locking up the feasibility. We have considered using a warm start. So a lot of the models, they're quite similar week to week. So we could probably just trim things down and just use a warm start. Some of our extended models, I think the warm start will have a big enhancement there. We did get stuck on a quality problem that was nonlinear for our transfer model, but and we were considering a warm start there, but we managed to solve that through other methods there. So, but beyond that, we really haven't gone much further into different heuristics. I suppose we are somewhat reliant on just trying different things within Gurobi. It's been fortunate for us. It's often been able to solve our problem. But I suppose as things get more difficult, we probably need to look into more advanced techniques and learn more about how they actually work. Like probably about 4 years ago, or maybe 3 when I started on this. Yeah, I didn't really know much about optimization at all. So I suppose that we're still learning as we go, and where we don't know everything. So yeah, we like watching all the other Gurobi webinars, learning things as well.
Yeah, just to add to the bit about the warm start, so not in this model, but another similar model which expands this. Another one of our colleagues, we have been investigating warm start and using that. So that's a particularly difficult quadratic problem. And what we found is that we have implemented this kind of logic where we will try find a solution as per normal, and then give it a little bit of a go, so to speak. And then if it's really struggling, we say, okay, well, now we'll just try flip to a warm start and see if that works as well. So we're just trialing lots of different techniques like that.
Thank you everyone for joining us today, and a special thank you to Toby and Philip. We are reaching the end of the hour. Thus, we will be getting back the rest of the Q&As via email post the webinar. We will greatly appreciate your feedback. After I have ended the webinar, if you can help us to do a short survey, that will help us to understand your thoughts, and if there is anything we should be improving for our future webinar, please feel free to give us a feedback. Thanks again, and we hope to see all of you in our next webinar. Bye-bye.